Hello, this next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 9 of a little mini series in split plot designs. And we're going to look at the F test. Now the model we're looking at is a split plot RCB, randomized complete block. That means the type of design that was used for the first factor. And I'd encourage you to watch parts 1 and 2 for more detail. But the model is this. It's Yijk is equal to mu plus epsilon plus beta, the error term associated with the whole plot, the first randomization, gamma, the interaction between alpha and gamma, and then the error term associated with the split plot, or the second randomization. The errors are normally distributed, mean zero with constant variances. They're independent. And this is a diagram of what it is. Now, each of these should be, randomly generated. So you randomly put treatments and etc. But then you can kind of reorganize it like this. And if you think of this as a block, and each one of these big sections within a block is a whole plot, and then these are the split plots or the subplots within the whole plot. Now, there's an overall effect for the first factor, alpha 1, alpha 2, and alpha 3. So that's this effect, and this effect, and this effect. And the gamma is, the effects for the second factor. So these are there's, for instance, 4 levels. And so this would be the effect for level 1, level 2, level 3, level 4. And then we also allow for interaction effects. So these could change individually. And so there's an alpha gamma 1 1, alpha gamma 1 2, etc. Alpha gamma 2 3, alpha gamma 3 4, 3 4. And when we conduct these tests, right, at first they're not going to seem intuitive, but they are. So if we want to test that there's no alpha effect, so it means that all of these are equal, and they're equal to some value, called the mean of the alphas. So if all the alphas equal to that overall mean, then there's no effect. But isn't that so this alpha effect is here, right? The effect from this whole plot is the same as this whole plot. It's the same as this whole plot. But isn't that the same as that if we look at the average effect across these, that has to equal the average effect of, across these subplots and the average effect across these subplots? And the answer is yes. And so when you see the hypothesis test, you'll see why we have to write it like that. Now, when we want to test that there's no gamma effect, so this has to equal this, which equals this, which equals this. So it equals something called the mean gamma effect. So these all have to equal. But this right here is representative of the gamma 1 effect. But isn't that the same that the average of these interaction terms have to equal the average of these interaction terms, right? For the gamma 1 to equal gamma 2. And the answer is yes. Now, to test block, which we usually don't do, this block has to equal this block, which has to equal this block, so that they have to equal some grand mean of, the beta mean. Now, for there to be no interaction effect, then each one of these has to equal itself, has to equal some overall mean, right? So if this is equal to the mean for the mean vector for alpha gamma, then there's no effect here. But that's sort of saying that, like, if that's true, then the mean of this the mean of each row has to equal that overall effect, and the mean of each column has to equal that average effect. Okay, and now let's look at that's my intuitive feel for what is going to happen here. So there's no alpha effect, right? So So the alphas all have to equal some overall effect. And then the average of these, interaction terms have to equal the average of these interaction terms. And that's what this piece is saying. In order for there to be no effect, those have to add sum to 0. If there is an effect, hey, something in there is not 0. And this is for some I. This has to hold for all I. So now we look at the F Test Statistic. So the mean squared error divided by this constant we showed was a chi-square distribution. And the same way, the sum of squares error for the whole plot divided by this same constant is also a chi-squared. And it's nice that those constants cancel and we're left with the mean square for alpha and the sum of squared error for whole plot. And that's it. And so this is a chi-squared with t minus 1 degrees of freedom divided by its degrees of freedom. Now this, of course, under the null hypothesis that there's no effect. So the non-centrality parameter is 0. And this one is always a central chi-squared distribution. So it's an F test. Well, and that's assuming these, the numerator and denominator are independent. And we show that in order for quadratic forms to be independent, then the product of these middle matrices have to be 0. And when you multiply this out, you do get 0, so these are independent. And this is the F test for no alpha effect. Now, the test for no gamma effect, it's very similar. We want each alpha parameter to equal some overall mean. That means there's no effect. But that's the same as if we were to sum, down across the interaction terms. All those averages have to equal some overall mean for those interaction terms. And they all have to be 0, and this for every k. And the null hypothesis is that, hey, something is not 0 for some k. And then we do the same. But notice the denominators here. The mean square for gamma divided by this constant, mean square error for the split plot divided by this constant. Each of those we showed in the previous video are chi-square distributions. This is a non-central chi-squared under the alternative, and it's a central chi-squared under the null hypothesis. Those constants cancel and we're left with this. And again, it's a chi-squared divided by its degrees of freedom, chi-squared divided by its degrees of freedom. That's actually with those constants in there, but then they cancel. To show that numerator and denominator are independent, we show that the product of those matrices is 0, and it is. And if you do the math, the FOIL it out method, then you'll show that it's 0. And the crazy thing is, these matrix multiplications is exactly what we're going to see when we do the R illustration. They're 100% the same. Now, no alpha gamma effect, so there's no interaction term, then this has to equal 0. And the way that this can be rationalized out is if we add and subtract 0 to this piece here, so we add and subtract this mean, then we take each term ij and then it's minus the mean, the overall mean, it has to be 0. And then we take the positive, that was the negative piece of this. The positive we could put with this, and that says that each row, the sum of the mean of the rows has to equal some overall mean. And then this right here, those have to equal, right? The column means has to equal some grand mean. So anyway, but two of those cancel and we're just left with this. And the alternative is that they're not 0 for some I or k. And the test statistic, it's an F. So the mean square for alpha gamma divided by this constant, sigma s squared, divided by the mean squared error for split plot divided by that same constant. These are both chi-square distributions. Under the alternative, this is a non-central chi-squared. Under the null hypothesis, it's a central chi-squared Those constants cancel. We're left with this, and it's a chi-squared divided by its degrees of freedom. Same here. Now, it's an F test only if the numerator and denominator are independent. And if we take the product of these two matrices, we do get 0, so it is independent. And again, all these crazy matrix multiplications will exactly equal what R produces. And we'll do that in the next video, part 10 of 10. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.